Anwesha Sahu. I am the Outreach Officer for AstroSoc, and thank you everyone for joining us in our third talk in the series Quarantine Talks. I'm currently doing my BSc in Physics with Particle Physics and Cosmology at the University of Birmingham, and I'm expected to graduate in 2022, so I'm heading into my second year right now. And I just thought I'd start off the talk with a little introduction about myself. I'm from India and Tanzania, so I was born in India, raised in Tanzania, and this is my first time giving a talk for AstroSoc, and I look forward to sharing the topic at hand today, antimatter and annihilation, with everyone around to view this talk. And this is something that I find really interesting, especially as a particle physics student myself. And there's several reasons why I love physics and particle physics. It pretty much started off as a quest to understand the universe's existence, which is why I chose to opt for particle physics as my BSc. And I was introduced to cosmology as a result of this by the time I reached around high school. But I'm going to steer away from philosophy a bit more, in the sense that I'm not going to try to explain the reason for the universe's existence. That's a very debatable question, and that's not the reason why I chose particle physics. But the reason why I enjoy physics and cosmology is because I exist. Why do I exist? Now, this is not a question for an existential crisis, but one of the most obvious observations is I am made of matter, like my laptop, on which I'm recording this talk for everyone right now, the Wi-Fi router, the YouTube headquarters, the University of Birmingham, and lastly, even you. We are all made of matter. And that precisely is the center of today's talk, antimatter and annihilation. So here's the outline for today's talk. We are going to be learning more about the Big Bang in a nutshell. We're going to discuss the matter-antimatter asymmetry problem, annihilation, and then we'll briefly touch on the concepts of charge, parity, and time, so CPT, and we'll look at CPT violation. We will look at the standard model's predictions, and we will look at the general model, which is a possible solution, perhaps, to the standard model's flaws, I guess. So with no further ado, let's get started. Around 13.7 billion years ago, it's said that the universe was created in a massive explosion called the Big Bang. The Big Bang itself was a singularity, and when the universe was extremely young, around a billionth of a trillionth of a second, it expanded rapidly in this process called inflation. And the universe literally grew exponentially, absolutely rapidly, and doubled in size at least 90 times. As it expanded, it got cooler and less dense, and eventually this rate of expansion started slowing down a bit, and the matter that was there then started cooling. The universe started cooling, and you could see matter coalescing. But then at that point, within the first 3 minutes of the universe's formation, the first thing that was formed was deuterium, which is an isotope of hydrogen. Much of this deuterium was eventually able to recombine to form helium. However, during the first around 400,000 years after the Big Bang, the intense heat from basically the formation of the universe made it very, very hot for light to shine. So it was essentially as if the light was bouncing around, so no light was effectively able to escape, and it was pretty much just an opaque plasma. And it was like, you can call it a primordial fog or a primordial soup in a way. However, after this phase, during the phase of recombination, free electrons were able to be absorbed by the atomic nuclei, and the universe eventually became transparent. And the light that was sort of released at this time is detectable in the cosmic microwave background, which we can see on the left side of this slide. So we can see that that is the cosmic microwave background, and this was the image that was basically captured by the Planck satellite, which is the most up-to-date image we have of the cosmic microwave background. So as the universe cooled and expanded around the time of 3 billion years, you can clearly see structure formation beginning to occur, and eventually we arrive at the stages that we are at today, 13.7 billion years, and we can see clusters of galaxies form, so the universe that we see around us. And that is basically the Big Bang Theory in a nutshell. Let's take a pause for a second. Well, cosmology and particle physics tell us that at the start of the universe, matter and antimatter were created in equal amounts. However, when matter and antimatter come together, they annihilate each other, so they destroy each other, leaving out a burst of energy. So let's take a pause for a second and just let's look around us. So in the top left side, we can see the Hubble Deep Field, which is a collection of stars and galaxies that we can see. And then we have the Earth. And the bottom picture shows the city that I grew up in, Dar es Salaam. And what's one of the obvious things that comes to one's mind when we see all these pictures? They're all made of matter. They are literally all made of matter that we can see, touch, and feel. Maybe we can't really touch the Hubble Deep Field, but we can see it, and we know that it's made of matter. And that precisely is the issue. If the early universe had equal amounts of matter and antimatter, why is it that everything that we see around us is just matter? What happened to all the antimatter? Where did it go? Why are these scales more why are they tipping more towards the matter side than the antimatter if they were created in equal amounts in the Big Bang singularity? So in a nutshell, equal amounts of matter should have been created in the Big Bang, but matter quite evidently is dominant. Matter particles and antimatter particles have the same mass, but some key qualities such as the electric charge or spin, for instance, have opposite signs. At the start of the universe, so now we're talking about literally the first few microseconds or billions of nanoseconds, particle and antiparticle pairs in the universe, they pop into existence and they destroy each other. And as they destroy each other, basically we have annihilation occurring, and this results in a release of energy, which effectively means that if this had happened, the universe should have nothing more than just a sea of energy at this point. But as we can see, roughly one matter particle in every billion particles survived this cosmic churner. And this results in the crisis of the matter-antimatter asymmetry. We can naturally detect antimatter today. It's not as if there's absolutely no antimatter observable in the universe, and probes have detected significant amounts of antimatter. For instance, with the cosmic rays. They contain a small amount of positrons. However, this isn't a solid explanation for why there's more matter today, or where the antimatter disappeared. The positrons that we observe with observatories such as the Fermi Space Observatory, as you can see in this picture, they can be explained by astrophysical processes, and these are perfectly possible in a matter-dominated universe from various different processes. And as a summary, we can see that annihilation is basically when matter and antimatter come across one another, they destroy each other, emitting a flash of energy. Now, this is a very active field of research that's going on in various physics facilities across the world. And as we can see in this image, this is the antiproton decelerator at CERN, and it produces antiprotons, and they carry out antimatter studies. This brings us to the next part of today's talk, which is Charge-Parity-Time, or CPT. These three symmetries are fundamental and crucial to nuclear and particle physics, and that these are parity, time reversal invariance, and charge conjugation. Effectively, these three symmetries address the following. So whether or not a nucleus behaves in a different way if we reverse the spatial conjugation or configuration. For instance, as we can see in the central image, whether the nucleus is spinning clockwise or anti-clockwise, and this is parity. And secondly, it deals with the question of time, whether we're moving forward in time or backward in time, and how this change in direction in time impacts the behavior or evolution of the system. And thirdly, it deals with charge conjugation, which is whether the particles are matter particles or antimatter particles and how they behave when we switch between the two. As we know, when particles and antiparticles come together, they annihilate and their resultant mass is converted into energy. So basically, matter-antimatter comes together, they destroy each other, releasing a burst of energy. Most of the time, this is in the form of gamma rays. And this symmetry is quite crucial to particle physics. In most circumstances, CPT is conserved. However, when this was extensively studied, it was observed that this symmetry is not conserved in every physical process. Let's look at the case of parity violation first. Particles have a property called chirality. Whether a particle has left-handed or right-handed chirality has a direct impact on its behavior. Left-handed electrons possess the weak hypercharge, whereas right-handed electrons don't. What this implies is that only left-handed electrons, or left chiral fermions, feel the weak nuclear force. And this asymmetry is parity violation. As we discussed, parity is when there's a change in its orientation, so basically like clockwise or anti-clockwise. This is a similar case. We don't really understand at the moment why the universe would be so affected or impacted by this, but it clearly does seem to be impacted, and this can be seen in particle behaviors. This weak hypercharge comes from the Higgs field, which seems to be an infinite source of weak hypercharge. Effectively, now this means that since only right chiral antifermions or left chiral fermions feel the weak force, Cp as a whole, so charge and parity, seem to hold. But parity violations hint towards the tau theta problem. And this is the next thing that we're going to discuss, which is the tau theta problem. The tau theta problem involves the study of positively charged kaon mesons. And this was a study conducted by James Cronin and Val Fitch, where they studied neutral kaons. Neutral kaons are effectively a mix of their own particle and antiparticle, namely the Ks and the Kl. The Ks has even Cp, which implies that it does not change when a combined Cp transformation is applied, and it is short-lived. Kl, on the other hand, is long-lived and has an odd Cp state. In a perfect world, Ks and Kl should not transform into one another because they have different Cp symmetries and different lifetimes. So what Cronin and Fitch did from this hypothesis is they sent both of these down a tube. What they expected is for the Ks particle to not have made it to the detector at the other end of the tube. However, they did detect some Ks particles. What this means is that the Kl particles oscillated or transformed into Ks particles, and this quite evidently shows that charge parity conservation was violated. So, as parity is violated, Cp is violated. Now, does that mean that time has to be conserved? Not necessarily. Time must be violated because the time reversal operation is necessary to bring the broken Cp reflected universe to a fixed Charge-Parity-Time universe. So the time transformation must break this symmetry in order to bring it to the broken universe in the first place. Effectively, this shows that if matter and antimatter can annihilate each other, and CPT violation and CPT symmetry can be broken, perhaps the standard model might be slightly flawed. In the standard model, the matter-antimatter asymmetry problem is linked to baryon asymmetry. So whereas standard model predicts a symmetric universe, during the cooling after the Big Bang, as we have discussed, the physical processes resulted in the scales tipping a bit more to the baryon, or matter, side of the scale. And this baryon number, essentially, may be violated with a set of 3 conditions, and this was set by quite a well-renowned physicist, Andrei Sakharov, who's a Russian physicist, and he set out 3 conditions, which is the baryon number violation, the CP symmetry violation, which we discussed, and the processes that occur should not be in thermal equilibrium. Now, whereas the standard model does provide physical processes where the 3 outlined conditions can be satisfied, the processes do not explain matter-antimatter asymmetry. The detailed explanation is beyond the scope of this talk, and hence, in physics, we have the need for theories that are beyond the standard model. And this brings us to quite an exciting new model, which is the generation model. This is quite a nice alternative to the standard model. Instead of the standard model's 9 quantum numbers, this utilizes 3 additive quantum numbers: the charge, the particle number, and the generation quantum number. All 3 numbers must be conserved in leptonic and hadronic processes, leptonic being the ones involving electrons and neutrinos and muons, and hadronic being the larger particles. It basically suggests that the antimatter created in the Big Bang is now stable, and it's contained in composite leptons and stable composite quarks, which basically says that antimatter and matter, they're still symmetric and there is no asymmetry. With this one might say that, well, what about the observed hydrogen-antihydrogen asymmetry? This can be observed and it can be explained quite well statistically because of the fluctuations in the formation of hydrogen and antihydrogen atoms. In a nutshell, perhaps we do have an explanation for why there appears to be a matter-antimatter asymmetry, whereas this model predicts that the antimatter has not really gone anywhere. It's still present, it's just contained in composite leptons. And more detailed studies of the generation model or more detailed readings into this model will provide a very detailed explanation of why this is the case. This brings us to the end of today's talk. I hope you enjoyed it, and I will be around at the Q&A session after following the end of the talk, and I'll do my best to address any questions that you might have. Thank you very much for joining, and I'll see you.
Give me a thumbs up when we're live.
Yes, I'm trying to figure out. Why does this say that? Okay, we're good.
Hello.
We're good.
It looks like everything is working. So welcome everybody. It's great to see you back here again. We have just had a fantastic talk from Anwesha, which was really enlightening. And I see that we've already got a question on the chat. As per last week, if you do have any questions about the talk material or any other questions that you fancy asking Anwesha, then please put them in the chat and they shall be read out, and hopefully we'll try and get the answers to you. So without further ado, I'll jump straight to the questions. So the first question we've got is, does the generation model also provide some explanations for other problems that the standard model has?
Thank you for the question, and I'd like to start off by thanking everyone who joined the Q&A, the talk, and yeah, I'm going to start addressing the question now. So I'll probably start off by discussing some other problems that this standard model has. So one of the other problems that the standard model has is, for instance, it deems neutrinos as massless, which is not entirely true because neutrinos have been observed to oscillate, which proves that they experience time and hence they do have mass. And yeah, regarding the CP violation and the points discussed in the talk precisely with the matter-antimatter asymmetry, At the moment, I am unaware of the detailed explanations for the other problems, such as the neutrino mass problem that the standard model has, or for instance, the standard model's issue with the lack of explanation of the graviton. But yeah, at the moment, I do not really have a very clear idea of whether or not it has explanations for these other problems. But if you're interested, you can send an email to the AstroSoc email address. One of the committee members will leave it in the comment section, and I will get back to you with more information as I come across it. Thank you.
That was brilliant. Thank you. We don't have another question on the chat at the moment, so I will jump in with a question. You mentioned the generation model, including composite electrons and composite neutrinos. As far as I'm aware, there's been no real evidence for any further substructure to these fundamental particles. What kind of energies would we have to probe at to explore this regime? And are there any particular candidates, theoretical particles that have been thought up that might actually constitute these particles?
Thank you for the question. And regarding the energy ranges, I do not have an exact range, like in terms of a number for which energy ranges we would look for these particles from. But from the research that has been done in the past, these particles, for instance, we would have to probe in deeper than the energy levels that we have, because when we are talking about these composite, structures, we are looking at structures effectively that are beyond the quark level. So we have to probably, this is kind of like an off the top of my head guess, so do not take my word for it precisely. But yeah, it would be higher energies than necessary for studying quarks, because we would have to look for substructure within them.
So am I correct in thinking off the back of that then that potentially this generation model predicts the quarks themselves contained in other hadrons, so things like your proton and your neutron? Would they have a similar substructure, or would they be still separate and still be fundamental in themselves?
I believe they might be fundamental in themselves, but then the key things, for instance, let me just get my presentation up in a second. That'll probably help me address this better. There we go. Yeah, but then the three main things that we have in the generation model, they would be the fundamentals. So, sorry, just a second. Yeah, so the charge, the particle number, and the generation quantum number would pretty much be present when in explaining the protons and the neutrons. So their behaviors would still be the same. But as far as the difference in structure is concerned, I do not have a very clear answer exactly, so I do not want to give the wrong information, but I can address that question at a later date if that's all right. Sorry about that.
No, that is perfectly fine. We don't seem to have any other questions at the moment, and I can say that I personally don't have any other questions either. It was a very, very well given talk. Is there anything else you would like to elaborate on regarding the topic, or perhaps why you chose physics, why you are a part of AstroSoc, and how your studies of particle physics kind of also link to astronomy?
Definitely, I'd love to do that. So I'll start off by explaining perhaps why I chose particle physics and cosmology at the University of Birmingham. So it essentially, as I explained in the talk, I always had this curiosity in understanding how the universe works at the fundamental levels. For instance, we know that there was a Big Bang, and we know that started off the universe. However, what we do not know for sure is how did the Big Bang exactly occur, in the sense that what did we have in the universe before the Big Bang? And that was one of the most pressing questions which I had during high school, following which I was introduced to cosmology. So that's how I came across the multiverse theory and the ekpyrotic theory, which is my personal favorite. And yeah, eventually, as I worked my way across that, I've realized that particle physics and cosmology tie in pretty intricately, because in the early universe, you really cannot, distinguish between the two. So that was kind of my main inspiration behind choosing particle physics and cosmology. And my involvement with AstroSoc and how it relates to my degree in particle physics and cosmology. I mean, the main factor that I think many physics students would agree with is probably that, I mean, physics is such a broad subject, in the sense that, I mean, particle physics and cosmology and astronomy have so many ties together. For instance, if we think of experimental or observational cosmology, that ties in pretty closely with astronomy. So a lot of the things that we study in astronomy, such as galaxy evolution, and for instance, like in the talks that we've had in the past 2 weeks with quenching galaxies and ultra diffuse galaxies, in the larger picture, understanding how galaxies would evolve, how the larger structures evolve, such as like the Lyman alpha webs and stuff like that, that would eventually answer the question of, how is the universe going to evolve in the future? Are we going to have a big bounce that, as certain cosmological models, such as the ekpyrotic theory suggest, or is it eternal inflation all the way around? And that's how I feel like astronomy links very closely with particle physics and cosmology. And that's one of my inspirations for my involvement with AstroSoc as well.
That is brilliant. Thank you very, very much for your answer. If we don't have any more questions, I'm either going to open it back up to you, Anwesha, and you can keep talking about whatever you wish, or if not, then we will look at ending this Q&A session, and we'll see everybody next week.
In terms of regarding the talk specifically, I don't really have anything to add in particular, but this is just from the email I think that was sent out to the AstroSoc mailing list earlier today. I just realized that that in the bio I had written my website, and unfortunately I think the link does not work for the website. And yeah, if it's okay, then I can either just type in the link for the website in the comments here, or I could send out an email or something.
Yep, no, that sounds really, really good. We'll definitely look at promoting that, so we can try and edit both the YouTube description, perhaps put the link in the chat as well. And if people would like, that can be emailed out as well to both mailing lists that receive the emails regarding these talks.
Perfect. And I'll just type it in the chat.
Brilliant. So while that is being done, I'd like to thank you once again, Anwesha, for the fantastic talk, and thank you everybody for coming to join us. As advertised, we have another talk next week, same time, same place, and we look forward to seeing you then. Thank you.
Thank you.